So, Melanie, I would suggest we start. And I've got the pleasure and the honor to speak the opening words. And I'm Franz Rudloff, and I'm CGECCO chair. And as chair of CGECCO, I want to welcome you all to the CGECCO chair lecture. As you all know for sure, that CGECCO is ACM's special interest group on evolutionary computation, which is the organizational body behind GECCO. And established in 2016, 5 years ago, the CGECCO chair lecture is a series of lectures sponsored by CGECCO to take place on the very last day of the GECCO conference, so today on Wednesday. And what it does, it recognizes influential researchers in the field who made a seminal contribution. And since 2016, chair lectures have been given by Stephanie Forrest in 2016, who was, for example, also a former co-worker of Melanie, by Hotel Lipson in 2017, by Dave Goldberg in 2018, by Ingo Rechenberg in 2019, and last year by the first CGECCO fellow, Darrell Whitler. And now, in 2021, I'm happy and proud to introduce Melanie Mitchell as invited speaker. Let me introduce Melanie. Melanie is since last year, she's a Davis professor at the Santa Fe Institute, where she also has an external professorship before since 2000. And in parallel, she was and still is currently on leave, professor at the Portland State University in the Department of Computer Science for more than 15 years. And in Santa Fe, Melanie originated, for example, the Complexity Explorer platform, which offers online courses and other educational resources related to the field of complex systems, which is a very helpful link in times of pandemic. And the online course, Introduction to Complexity, has been taken over by more than 25,000 students and is one of the top 50 online courses of all time in this course program. Melanie has also a very active research program in artificial intelligence, machine learning, biologically inspired computing like evolutionary algorithms, cognitive sciences, and complex systems. If you look at metrics, Google Age Index is 48, and your papers have gathered in the last years more than 30,000 citations. For example, very prominent is a 98 book, Introduction to Genetic Algorithms, which is one of the standard classical books for GAs, with alone more than 16,000 citations. Or her book 10 years ago on Complexity, a Guided Tour, which won in 2010 the Phi Beta Kappa Science Book Award, and even Amazon, who is sometimes also known for books, selected it as one of the 10 best science books in 2009. And then her latest book, because Melanie is a very active book writer, that I also like a lot. Her actual book deals with artificial intelligence, a guide for thinking humans. And this book also shows us the direction, I use now her words, to where AI systems become more robust, general, and adaptable. In short, more intelligent. But now it's a time to hand over to Melanie. I'm looking very forward to the talk, where she tells us why AI is harder than we think. Of course, we all know this by experience from the last years and from all our experiments that didn't work out. But the nice thing is that Melanie will put some evidence to her experience. And to all of you, enjoy the talk. Melanie, the stage is yours.
Thank you, Franz. Thank you so much for inviting me. Very happy to be here. Many of you have probably been hearing for a long time that we're going to have self-driving cars any day now. In fact, last year, 2020, was a year when many predicted that we would have widely deployed self-driving cars. We were told that 10 million cars would be on the road by 2020, and even Elon Musk, the CEO of Tesla, told us in 2019 that we'll have over 1 million cars with full self-driving software, everything. However, that hasn't happened. And one AI researcher had this to say: perhaps expectations are too high and this will eventually result in disaster. Suppose that 5 years from now, funding collapses miserably as autonomous vehicles fail to roll. Every startup company fails and there's a big backlash. So you can't get money for anything connected with AI. Everybody hurriedly changes the names of their research projects to something else. This condition is called the AI winter. Well, as it happens, this quote is actually from 1984 by AI researcher Drew McDermott. And you can see that these kinds of situations in AI, the AI spring, when we're all very optimistic about the progress of AI, oscillates with AI winter, when this kind of disappointment leads to reductions in funding and general kind of malaise about the state of AI. And we've seen several of these cycles between AI spring and AI winter. We're clearly now in an AI spring when many people are quite optimistic, but some have predicted that we're headed for an AI winter, and the self-driving car kind of disappointment is one of the symptoms. Well, we've seen confident predictions since the 1960s about the state of AI. Claude Shannon himself, the founder of information theory in 1961, predicted that within 10 to 15 years, we'd have something like what we see in science fiction movies. Herbert Simon, Nobel Prize winner, believed in 1965 that within 20 years, machines will be able to do any work that a man can do. Well, back then, I guess man meant man, but the sexist language notwithstanding, he was very optimistic. And Marvin Minsky, founder of the MIT AI Lab in 1967, said that within a generation, say 25 years, the problem of creating AI will be substantially solved. Well, none of these predictions actually came true. And many years later, one of the founders of AI, John McCarthy, said that the problem is that AI was harder than we thought. Well, true enough. But why is AI harder than we think? Do we still think that AI is, are we still sort of optimistic in an unrealistic way about the prospect of AI? Well, we've seen some more recent predictions, like from Shane Legg, the co-founder of DeepMind, predicted that human level AI would be passed in the mid-2020s. That's actually pretty soon. Mark Zuckerberg said that one of the goals of Facebook within the next 5 to 10 years from 2015 is to get better. He means machines to get better than human level at all the primary human senses: vision, hearing, language, and general cognition. And Stuart Russell, professor at University of California, Berkeley, in his recent book on called Human Compatible, asked, when will super intelligent AI arrive? It will probably arrive in the lifetime of my children. And he says that that's actually a more conservative estimate than that of the typical AI researcher. So we are still getting some optimistic predictions about AI. But I want to argue that AI is still harder than we think. And the reason is at least partially because of 4 fallacies that people in the field and outside the field still believe about AI. Fallacy one is that narrow AI is on a continuum with general AI. So this is a fallacy that we believe that if we make giant progress in narrow AI, that we're also making progress, we're making steps towards general AI. So for example, IBM in one of its press releases described its Watson system as a first step into cognitive systems, a new era of computing. DeepMind, who created AlphaZero, has said that it's a giant step in AI progress, and others have called it a first step in creating real AI. And OpenAI's GPT-2 and now GPT-3 has been described as a step towards general intelligence. So this idea of what these first steps was what the philosopher Hubert Dreyfus called the first step fallacy. And he wrote this several decades ago. He said that it's the claim that since our first work on computer intelligence, we've been inching along a continuum at the end of which is AI. So any improvement in our programs, no matter how trivial, counts as progress. However, he points out that there's actually a discontinuity in this assumed continuum. The unexpected obstacle was called the common sense knowledge problem. And I'll talk more about that later. But what Dreyfus is saying is that believing that all of these are steps towards general intelligence, these will all actually meet the barrier of common sense knowledge. His brother, Stuart Dreyfus, an engineer, made an analogy. He said, it's like claiming that the first monkey that climbed a tree was making progress towards landing on the moon. So the second fallacy is that easy things are easy and hard things are hard. Okay, so this is saying that the things that we humans consider easy, we assume will be easy for computers as well. And the things that we consider hard will be hard for computers. So Herbert Simon said that he believed everything of interest in cognition happens above the 100 millisecond level, the time it takes to recognize your mother. So what he's saying is that all of sort of basic perception and recognition, the things that we can do within 100 milliseconds are not that interesting. What's interesting is the higher level things that we do, such as reasoning, that are slower. And this was his idea, that we could ignore a lot of the basic perception in AI and just tackle the reasoning part. And that way we would get to general intelligence. More recently, the AI researcher and entrepreneur Andrew Ng echoed Herbert Simon. He said, if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI either now or in the future. So this is kind of a dismissal of the difficulty of the fast unconscious kinds of thought that we humans do within the first second of thinking. A subtle version of this is Demis Hassibis, one of the founders of DeepMind, who said that Go is one of the most challenging of domains. But the question is, challenging for whom? It's certainly challenging for humans. It's very rare to have people who can play Go at a very high level. But is it one of the most challenging of domains for machines? In an article discussing the AlphaGo and so on, the psychologist Gary Marcus pointed out that simpler games, quote unquote simpler games, such as charades, which any 6-year-old can play, is actually much more challenging for machines than Go, because it involves issues of language, theory of mind, and all kinds of other skills that are very far from what we are able to have computers do today. And all of this you may recognize as Moravec's paradox. Hans Moravec was an AI researcher who wrote in a book about AI that it's actually comparatively easy to make computers exhibit adult level performance on intelligence tests or playing checkers. And here today we might say playing Go. And difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. And I would add, and common sense. So Moravec's paradox is that easy things for humans are hard for computers. And one of the reasons that we believe that we're so close to AI is that these things are so easy for us. We still believe it's not going to be that hard to get computers to do them. And Marvin Minsky said this another way. He said, in general, we're least aware of what our minds do best. The third fallacy I call the lure of wishful mnemonics. And it's maybe not technically a fallacy, but it's certainly a reason why people fool themselves about the prospects of general AI. And again, Drew McDermott was the one who coined this term, wishful mnemonics. He said, back in 1976, if a researcher calls the main loop of his program understand, he is, until proven innocent, merely begging the question. He may mislead a lot of people, most prominently himself. What he should do instead is refer to this main loop as G0034 and see if he can convince himself or anyone else that G0034 implements some part of understanding. He called this a wishful mnemonic. And he said many instructive examples of wishful mnemonics by AI researchers come to mind once you see the point. So this idea, and this was in a wonderful paper McDermott wrote called Artificial Intelligence Meets Natural Stupidity. And I think if you haven't read it, I highly recommend it. It's very short and very insightful. His point is that we tend to anthropomorphize what our machines do. We call them, we describe them using terms that mean something to us, like understand, but actually are not some really corresponding to what the program itself is doing. So there's a lot of, if you look around, there's a lot of examples of this in modern times as well. For example, today's benchmark data sets for AI and machine learning are, we call them things like reading comprehension, common sense understanding, or general language understanding evaluation. This is the last one, which is called by its acronym GLUE, is a widely used data set for testing the general language processing abilities of natural language processing systems. But we call it general language understanding evaluation. And then when machines do well on it, we assume that they have accomplished general language understanding. So this is really a wishful mnemonic. But however, a lot of people have shown that even though machines can do well on these data sets, they aren't actually accomplishing the abilities that are in the names of the data sets. So in this paper, Shortcut Learning and Deep Neural Networks, Giros et al. Said that we must not confuse performance on a data set with the acquisition of an underlying ability. In fact, the machines often learn what they called shortcuts, that is, ways to do well on a particular data set using particular statistical associations that might be subtly present in the data set without actually attaining the ability in the data set's name. So I call these wishful mnemonics. Even as going as far as calling our methods deep learning or neural networks, we are assuming that these systems are doing something like learning in the human sense, or neural, they're neural, they're based on the brain. Whereas actually the kinds of learning that these systems do and the kinds of brain-like structures that are in these networks are extremely different from the real world, what humans do in learning and human neural networks. So we sometimes might fool ourselves that machines are quote unquote learning on their own with machine learning when they're actually not doing anything like what human learning is. And there's many examples that you might call over attributions in descriptions of what machines have learned. One example that I found really interesting was in the field of deep reinforcement learning. For instance, Google DeepMind had a machine, deep Q learning system, deep reinforcement learning system that learned to play the Atari game Breakout. And here you have, in Breakout, you have a paddle that you move around, and there's a ball that the paddle bounces off the paddle and is used to collide with and explode the bricks here. These are all, on the screen. And their system learned a really clever strategy, which was to create a tunnel through the side and bounce the ball along the wall here to automatically, without having to move the paddle, destroy the highest value bricks. And here's how they described it. After 600 episodes, the deep Q network finds and exploits the optimal strategy in the game, which is to make a tunnel around the side and then allow the ball to hit blocks by bouncing behind the wall. Seems fair enough. But notice the words that they're using: tunnel, ball, blocks, wall. These are all human concepts. And it's not clear at all that the algorithm actually has any concepts like that at all. That it's learning from the pixels of the video game, but these are human concepts. And by assuming that the machine has learned these concepts, we would assume, for example, that it would be able to transfer what it had learned to a simple variation of the game here, where the paddle is shifted up by a few pixels. If it knew about paddles and balls and tunneling and something, nothing really has changed here except shifting up the paddle. However, machines that were trained with deep Q learning or deep reinforcement learning on this version of Breakout were not able to transfer what they had learned to this version. So that really shows that they had not learned these human concepts of paddle, ball, tunneling, walls, etc. But they had learned some other kinds of pattern associations that allowed the machine to do well on the left-hand version, but not on the right-hand version. So if we over attribute what the machine has learned, we're going to be bad at predicting what kinds of failures the machines might have. So a few other examples of wishful mnemonics. IBM, talking about its Watson program, stated that Watson can read all of the healthcare texts in the world in seconds. And of course, read here means something very specific for humans. When we humans read, we can understand what we read and we can apply it in different situations. But what Watson is doing is something very different when it reads. It's actually doing some kind of processing of the text that is very different from human reading and predicts very different abilities. Watson understands context and nuance in 7 languages, and you might say this is all just the public relations department trying to convince customers to spend money on this product. But these things, as McDermott pointed out, can actually fool not only non-experts in AI, but we really can be fooling ourselves. AlphaGo's goal, this is a statement from DeepMind, is to beat the best human players, not mimic them. Well, does AlphaGo actually have any kind of goal in the human sense of goal? Does it even have the concept of beating the best human players, or even know what a human player is, etc.? And again, I apologize for beating up on DeepMind because they're a company I respect a huge amount in their AI research, but they do make some very easy quotable statements like this. We can always ask why AlphaGo, how well it thinks it's doing during the game. It was only towards the end of the game that AlphaGo thought it would win. And this gives the impression that AlphaGo actually has a thought, that it actually has a concept of winning in some human-like sense, and so on. So these are wishful mnemonics that can lead us to be over-optimistic about what our programs can do. And the question I have is this an inevitable shorthand or a misleading anthropomorphism? Okay, the fourth fallacy is that intelligence is all in the brain. Okay, this is something that, of course, this debate about sort of what is the seat of intelligence, where is intelligence, goes back for millennia. But AI has assumed that the brain is the right place to look for all of intelligence. And in fact, intelligence can be sort of sifted off the details of the brain, that it's really the patterns, some kind of pattern of symbol processing, according to Newell and Simon, with their physical symbol system hypothesis, where here their notion of a physical symbol system was something like a Lisp program. More recently, in a report on the computational capacity of the brain. The author stated that it's more likely than not that 10 to the 15 floating point operations per second is enough to perform tasks as well as a human brain. Of course, given the right software, which might be hard to create. So this is sort of saying we don't have to worry about anything else besides the brain. AI is kind of like a brain in a vat, using an old philosophical thought experiment, that there's no need for the body in any of this. Geoffrey Hinton, one of the pioneers of deep learning, proposed that to understand, say, documents at human level, we're probably going to need human level resources. And what he means by that is the resources of the brain. So he says we have trillions of connections in our brains. The biggest networks we have built so far have only billions of connections. So we're a few orders of magnitude off, but I'm sure the hardware people will fix that. So the idea here is, well, we just have to build networks that have the same kind of computational capacity as the brain, and then find the right software, and voila, we get general AI. And perhaps quantum computers will be the vehicle that gets us there. But this leaves out a lot of thinking about intelligence that says that it's not just the brain, but the body of an organism has a lot to do with its ability to think. Okay, so for instance, the psychologist Rebecca Fincher-Kiefer talks about embodied cognition. It means the representation of cognitive knowledge is dependent on the body. It's multimodal, not amodal, symbolic or abstract. It suggests that our thoughts are grounded or inextricably associated with perception, action, and emotion, and that our brain and body work together to have cognition. Similarly, psychologist Don Tucker, he's actually a neuroscientist, says that when we study the brain, when we look for the networks controlling cognition, we find that all of these networks are linked to sensory systems, to motor systems, to motivational systems. There are no brain parts for disembodied cognition. And finally, in the famous book, Metaphors We Live by Lakoff and Johnson, they noted that our thoughts and our language are built on top of metaphors about how we experience the physical world and the flow of time. That's the basis of how we think and reason. So I think it's a lot of AI has not really taken seriously the psychological and neural evidence that our bodies are a big part of the way we think. And we also might include our social, the embeddedness in a social system and culture. So some open questions that are spurred by these fallacies. If narrow AI is not on a continuum with general AI, how can we actually assess progress towards general or human level AI? If easy things are not easy for computers and hard things are not hard, how do we actually assess the difficulty of a domain for AI? How do we talk to ourselves about what machines can and cannot do without fooling ourselves with wishful mnemonics? How do we avoid anthropomorphizing our machines, what they do? And if intelligence is not all in the brain, how embodied or socially, culturally embedded does intelligence need to be? So I don't have answers to these questions. I think these are the kinds of questions we should be very seriously talking about in the field. And I think if we don't talk about them, we're going to continue to fool ourselves about how well machine AI is doing and how close we are to general level AI. So let me just talk a little bit about what I think are the major open challenges in our field. One of the first ones is what people call few-shot learning. Okay, that is learning from just a few examples. So for example, if I give someone who has never seen a bridge some pictures of bridges, they might be able to recognize new examples of bridges because they get the general idea that a bridge is a means to for a vehicle or a pedestrian to cross from land, one piece of land to another over water. So that you might get that idea. Okay, just with a few examples, not with millions of examples. Another open challenge is generalization. So once we learn the concept of a bridge, for example, we're able to recognize it even if it's quite different from ones that we've seen, largely because we have a sense of its functional properties. So here's a strange looking bridge. Here's a kind of inverted bridge where instead of cars passing over water, we have boats passing over a highway. So this is a water bridge for boats rather than cars. But we're able to generalize these concepts very easily. And this is sort of important, essential feature of human intelligence that we're still struggling to get into machines. Also, my own field of abstraction and analogy is still a major open challenge. So following on with the bridge example, once we've learned the concept of a bridge, we can generalize it and abstract it. We can recognize this ant bridge as analogous to human-built bridges. Ants are using this bridge made of their own bodies to cross from one surface to another. We talk about the bridging our hands, or the bridge of a nose, or the bridge of a song. We're able to abstract any concept like this analogously to extend what the concept means metaphorically, the way that Lakoff and Johnson mentioned. And this is really, I think, at the core of our ability to flexibly recognize and understand novel situations. Even more abstract, we might talk about bridging the gender gap. During the campaign, Biden said he was a bridge to a new generation of leaders, and we understand what he means exactly. We don't even necessarily consciously recognize it as a metaphor, but we can absolutely physically imagine him sort of bridging with his body from one generation of leaders to the next. And this is the way that we think, is in these kinds of abstract metaphors based on physical experience. And you can just go on, and really I will claim that you can do this with almost every basic concept. You can do these kinds of metaphorical extensions. And this is something that machines can't do now, and we really will need them to be able to do this kind of abstraction if we expect them to understand the human world. Hofstadter, in his paper Analogy as the Core of Cognition, defined a concept as a package of analogies. And you really can see why that's the case looking at the bridge example. Another major challenge is transparency and robustness in AI systems. So you might train your machine on thousands to millions of examples, and then maybe your machine does very well on a particular benchmark. But as I mentioned, sometimes the machine isn't learning what you wanted to teach it. So one example of this was a project one of my students did where he trained a deep neural network to distinguish between images that had animals and images that did not have animals. And it was trained on a bunch of nature photos, and the machine did very well on generalizing to a test set. But when my student actually tried to figure out what the machine had learned, and this was the topic of his dissertation, he found that one of the features the machine really focused on was the background, not the animal, because it turned out that if the background was blurry, like here, that was a good predictor that there was an animal in the picture, because of course the photographer is focusing on the animal, whereas in the no animal pictures, there's nothing to focus on, so the landscape background is clear. So this kind of shortcut is very common in machine learning. It's not at all transparent what these systems learned. This is also shown in a recent paper that took deep neural networks that were able to recognize pictures and objects like fire trucks with like 99% confidence. But if they photoshopped the object into some non-standard pose, the machine is very confident now that it's a school bus or a fireboat or a bobsled. So somehow the machine is using features of the image that are very different from those that humans would use to figure out what's going on. And it's not very transparent what these features are. And this means that sometimes these systems can not be very robust. You know, you've all seen examples of these adversarial attacks on vision systems, such as a system that can recognize stop signs very confidently. If you put certain adversarially designed stickers on the stop sign, now the machine is quite convinced that it's a speed limit 80 sign. And finally, I talked about common sense earlier, but this is really one of the most important and difficult challenges, is getting machines to have the kind of knowledge of the world that we humans have. So as an example, here's a highway in the northeast of the US in advance of a snowstorm, where the highway department has laid these lines of salt along the highway in advance of the snowstorm to keep cars from slipping. And a Tesla autopilot system, this was a tweet about how the salt lines were confusing the Tesla's autopilot system and couldn't figure out where the lane lines were, because it didn't have this kind of background knowledge of what these lines could possibly be. It didn't have the common sense that a human driver would have. We've seen these kinds of accidents where a self-driving Tesla will crash into a stopped fire truck on the highway. It's lacking the common sense that this is an obstacle. And more generally, I found out that self-driving cars, the most common accident that involves self-driving cars is that people rear-end them, meaning that the self-driving cars unexpectedly slam on the brakes and stop, and the human following them in a car crashes into them because they weren't expecting the car in front of them to stop, because there's nothing to stop for. There's no reason to stop, but the self-driving cars are somehow perceiving obstacles where there are no obstacles. So here, human drivers are at fault, but they're at fault because the self-driving cars are driving unpredictably. And they're stopping for things that no human would consider to be an obstacle, like, for instance, a plastic bag by the side of the road, or a tumbleweed, for example. Maybe a flock of birds crossing the road. Most humans would say, okay, the birds will fly away. I don't have to, maybe I'll slow down, but I don't really have to stop and wait for them to cross the road. Whereas you probably would, as a human, would have the common sense not to drive through a pile of glass on the road, or to stop and wait for this snowman to cross the street. We humans have a vast amount of knowledge about how the world works, and we use that in every situation that we're in. And how to get machines to have this kind of common sense is perhaps the biggest challenge of AI. It's what Hubert Dreyfus called the barrier that's blocking this continuum of narrow AI to general AI. And in fact, a lot of companies and institutes are looking at common sense now. The Allen AI Institute is focused on how to teach machines common sense. And the Department of Defense in the United States has a very robust funding program in trying to teach machines common sense. So here we have Moravec's paradox again. We can get machines to play games like Go and chess at a grandmaster level. We can get them to translate between hundreds of languages, but we can't get machines that have the common sense of a 2-year-old. So just as one example, consider this situation. this is something I talk about in my book. Suppose a self-driving car is faced with a situation like this on the road. What do they need to understand to make sense of what's going on here? Well, some core components of human understanding are things like intuitive physics, biology, psychology. We know how objects interact with each other. We know that what's going to happen when this woman pushes this stroller. We can predict how fast she's going to walk. We know what's going to happen when she pulls on this dog to cross the road. We have some theory of mind. We know that she's distracted, that she probably doesn't know this man, that they're probably not going to stop in the street and hug. And we know even more basic common sense things like that this man has legs, that he has to have legs to be crossing the street, even though we can't see the rest of his legs. We have just this vast knowledge about the world that we use to be able to predict what's going to happen next. And importantly, we use abstraction and analogy to take what we've learned in previous situations and map them to new situations. Way back at the beginning of AI, the Dartmouth Summer Research Project was one of the first meetings about AI back in this was the proposal for it, and it met a year later. But here's what they proposed to do. They were going to, during this summer, 2-month, 10-man study, they were going to work on how to make machines use language, form abstractions and concepts, and solve kinds of problems now reserved for humans and improve themselves. Of course, all of those things are still open problems in AI, especially this one, forming abstractions and concepts. And I think that's something that shown that machines are still very bad at doing, even when we use wishful mnemonics to convince ourselves that they have. And it's the most important problem in AI. Without concepts, there can be no thought, and without analogies, there can be no concepts, said Hofstadter and Sander. And I'll add to that how to form concepts and make analogies are the most important open problems in AI. So my book, Artificial Intelligence, A Guide for Thinking Humans, talks about this quite a bit more in great depth, if you're interested, and I'd be happy to answer any questions. Thank you for listening.
Melanie, many thanks for this very interesting and inspiring talk, and that clearly showed the limitations we have to deal with. And now I want to open the floor for questions. I basically scanned carefully the chat, but the only discussion was there this mnemonic on machine learning, which is a really funny one. But you basically addressed this also in your talk. Okay, there's one question from Juan. 1 second, I give you, okay, you could now ask a question. Did this work? No, it seems to me it didn't really work well, but then perhaps I want to bring up a question from the chat where Elvis Popovich asks, is artificial intelligence generally possible without ontologies?
Is general AI possible without ontologies? So it depends what you mean by an ontology. So an ontology usually means some kind of system of knowledge, some kind of knowledge representation. And I would say, yes, we absolutely, an general AI system needs some kind of system of concepts. As I've said, concepts are really important, and some set of relationships between concepts, but figuring out how to construct these ontologies, how to learn them, how they change over time? This is something that's the big open question in AI. You know, the deep learning revolution came about because in response to more statistical learning and symbolic AI, which really wasn't succeeding in learning the kinds of unconscious concepts that we have. And the idea with deep learning was, well, we won't try and program anything in, we'll just learn everything from the data, from massive amounts of data. But it seems, as I've shown, that there are some limitations to that it's very hard to learn and extend concepts with the kinds of architectures that we have now in deep learning. So I guess the answer is yes, but we don't yet know really how to do it.
But I was also thinking of, if you ask a 2-year-old baby, which is clearly an artificial intelligence, whether she has a concept of ontology, I'm not 100% sure. But there's another question from Peter Borsman. Because you have shown us all these predictions on the future and when there will be the general AI, but he asked, what is your own prediction for the development of a general purpose AI? Do you still believe in it? Will it happen? Or do you want to make, really now, we can even switch off the recording and basically cut it from the recording, but do you want to make any predictions whether it will happen and when it will happen?
Yeah, that's a question I get a lot. You know, I think even when we know that we're fooling ourselves about AI because of these fallacies, we still fool ourselves. It's hard to get out of that. So I think AI is harder than we think, even when we know that it's harder than we think. So it's hard to make predictions. I quoted somebody, an AI researcher in my book, who said that general human level AI is 100 Nobel Prizes away. Okay. And what they meant by that, was, you know, it's hard to predict, but when we're going to get the big breakthroughs that we need to sort of make sense of and build intelligence, we first have to understand intelligence, what it is. We have to have kind of a science of intelligence. There's been a lot of comparisons of current AI to medieval alchemy. You know, we're sort of pouring together these elements and trying to make gold, and we don't really have a theory of chemistry. So we're waiting for that theory of chemistry, which is really a science of intelligence. And that may be 100 Nobel Prizes away, I don't know.
Okay, so the 100 Nobel Prizes is a quite accurate prediction. But perhaps following this question, it's 100 Nobel Prizes away. Yeah, there's a question from Konstantinos Svikas who answers, could be some improvements or some answers to these open questions for these 100 Nobel Prizes gradually emerge through open-ended evolution and via interaction with the AI systems, or the interaction between AI systems or the world, or do you see the bridge or the canyon too far away that you could not really interact at the moment?
I think there's going to have to be some, you know, in order to gain intelligence, there has to be some interaction between an agent and sort of the complex environment, obviously. And the environments in which we build AI systems are often fairly narrow. Yeah. So I don't know how complex an environment has to be, but the question about open-ended evolution. So you know, that's, I think evolution, you know, people are now looking again at evolutionary computation as a viable method for getting to AI. But evolutionary computation, you could even argue, has some of the same fallacies that I mentioned about AI, that we use these terms in a way that makes us think we're doing something like evolution, biological evolution, but there's actually a lot of aspects of biological evolution that might be essential to build complex agents that we're missing. So the answer is, you know, I think that's evolutionary computation is once again drawing a lot of interest in AI. but there's a long way to go before we can really do this kind of open-ended evolution to get to complex systems of the kind we're looking for.
Yeah, yeah. Though basically, once the artificial intelligence is in a state that we can really interact with them, then it may be possible, but you still believe there's a hard way to go in this direction. For example, Dirk Tierens, that was also a question on my list, asks, basically you've written, you've had a strong influence on GAs, and looking back to your work in the 90s with the textbook, and he asked, what role do you see for evolutionary computation in getting better AI, or how can evolutionary computation help AI to become intelligent? Or do you see a role of evolutionary computation, or why do we need EC in another way? Or do we need EC, evolutionary computation, for evolving or for coming to a situation where we have artificial intelligence in a general purpose artificial intelligence?
So do we need evolutionary computation to get to general AI? Yeah, I don't know. I think that it's one promising method. You know, we talk about it. You know, we talk about comparing AI systems to like a 2-year-old. We've done that in this lecture before, but of course, a 2-year-old has the benefit of billions of years of evolution that have underlied the formation of the human brain, the human body, to be very well suited for a particular environment. And so there's a lot of innate structure there that may be absolutely essential for human-like intelligence. And it's not clear that we can engineer that structure. So we may have to rely on a kind of evolutionary process. The question is, will it take 1 billion or 4 billion years to get there? Well, perhaps not. Perhaps we can speed it up some. But I don't know. I think, you know, probably we need several Nobel Prizes worth of breakthroughs in our understanding of artificial evolution as well.
So, but this means that
oh, is Franz frozen? Franz's video seems
yes, indeed. Yeah, I'm afraid that's the case. So we'll probably try to replace him and find next questions on the list in chat. So I'm not perhaps sure which one was the exact, okay, the one that which Franz finished. So there's another question from Paul Murnau, from is general AI desirable? Would sentient machines have rights, or would they be slaves? That's of course a very general one, the general question.
Right. So like any technology, you know, AI has great potential to help our world, and it also has great dangers. And I think, you know, right now, so there's a question of like, what are the dangers of AI right now, where we don't have general AI, we don't have human level AI? There's already a lot of dangers that come with the biases of AI, the kinds of untrustworthy, unreliable, unrobust systems that we have that are being deployed. But then there's the question like, well, if we actually do achieve general AI, is that something we want to do? Is that something that's going to actually benefit us or hurt us? And I think there's arguments both ways, but really this is a discussion that we should be having. Although I do think this is like, there's some pressing current problems that are probably we need to deal with before we really focus all our efforts on thinking about the ethical implications of human level AI, since it's fairly far in the future, I would guess. Now, I've debated with people about this. I had actually a debate with Stuart Russell about the existential risk of super intelligent AI and how pressing a problem it should be. But I don't know. Like any technology we have, there's this great potential for benefits and great potential for harm, and we have to think about that. And think about that beyond the sort of computer science technology communities, and getting into the other communities, like people who think about social systems, people who think about legal and ethical issues in general. And so we really have to broaden the discussion.
Thank you. Now there's a question that might, I think, somehow relate to your book, Complexity. So there's a question from Colin Flynn. Is a high level of complexity much higher than at present a prerequisite for general AI?
So is a high level of complexity, like in our AI systems, a prerequisite for general AI? Well, it's a little hard to answer that, since we don't have a very rigorous definition of complexity or measure of complexity in AI systems. But I certainly think that, just as an example, most deep neural networks people use today are mostly feed forward. There's no feedback connections. Sometimes you can have recurrent networks, but that's very weak kind of feedback. Whereas the brain, for instance, in the visual system, there's 10 times more feedback connections than there are feed forward connections. So there's a huge amount of what you might call complexity in the brain networks that we aren't capturing in neural networks. And it seems like there's very important things going on there. So yes, I think we will have to increase the complexity of our the models that we're using, because we're missing a lot of really important aspects of how intelligence works in biological systems. But we don't understand that well enough yet to really figure out what's the essential parts and what's not.
Thanks a lot. I'm also trying to see if there are any questions from the audience. I can't see any raised hands, at least now. Oh, but I think Franz is back. Franz, would you like to take over again, or can you hear us?
Oh yes, I'm back. Sorry, somehow my router broke down and I have no clue what happened. Have you continued without me?
Yes. I've asked like 2 questions, but please continue perhaps the thread.
No, I would suggest you can continue, because that would probably too much.
Okay, good. So of course, let's of course perhaps share this somehow. There's another question that I personally find quite interesting, is the one from Dan Appledorn. In a keynote at Common Sense 2017, a central statement was something like, we need AI to be able to handle the concept of being contained, which is one of the key concepts, but to a lot of things that are important in the human world. What do you think about this?
So being content?
Contained. I guess the author may mean that self-contained, but I'm actually frankly not 100%. That's my guess, technically speaking.
Right. I think, I think the notion of containment, maybe they're talking about. So this is perhaps similar to my bridge example. I'm guessing at the meaning of this question, but all of these concepts, we have to understand metaphorically as well as literally, being contained. Like I could say that I have a bad temper, but I'm containing it. That's sort of a metaphorical use of the notion of containment. And again, I think that's absolutely at the core of what we mean by intelligence, is being able to extend these concepts in a way that we can make sense of situations in both concrete and abstract ways. So yeah, I think that's absolutely at the core of common sense, is this idea of these extensible concepts. And in fact, in other talks, I've said that what deep learning systems do is that they recognize perceptual categories like bridge. They might even recognize a perceptual category of containment in a particular situation, but what they don't have is these concepts. That is these much richer, more flexible, extendable, metaphorical systems of knowledge that we humans have. And that's really a challenge, is to figure out how to get machines to have that.
Yeah, thank you. There seem to be a range of questions actually that seem to relate to AGI. So let me perhaps read the first of them. That question comes from, from Maciej Świechowski, I think. I was wondering if you follow what Ben Gritzel and his team does, and if so, how would you evaluate their efforts, how far they are? I'm curious about their goals of getting close to AGI.
So Ben Gritzel?
Yes. I think
so I have followed them a little bit, but not enough to really answer the question very well. I know that they've been working on so-called AGI, but I don't think that they're very close to it yet. And I would guess that they would also agree that they're not that close, but I don't know. I don't know if Ben Gritzel is here in the audience or not. But I'm probably not knowledgeable enough about their work to say.
Okay. Yes, sorry, that was probably a tough one. Yeah? So good. So perhaps now we have some questions also now from Abdul Jarir Abdul Rahman. Is our ability or inability, is our inability to attain general intelligence in machines attributable to limited understanding of how humans learn, or it has to do with how to model it for machines?
I would say both. It's both due to our limited understanding of humans and other animals' intelligence and learning, and it's also due to our not knowing exactly how to model it in machines. So, you know, people have asked, like, why do we have to focus on human intelligence? Why can't we have something that's different, that's like machine intelligence, that's different from human intelligence? And I think in some situations, yes, we do want a different kind of intelligence. You know, people are using AI in sort of scientific discovery, where they're trying to get machines to find patterns that no human would ever see because of our biases. And that's I think, a great strategy. But then in other situations, like say self-driving cars, we want these programs to understand the world in the same way we understand it, so that they can interact with us, so that they can predict what we're going to do, so that they can generalize in the way that we generalize. So it sort of depends on what the application is, how human-like we insist that these systems can be. But in terms of sort of general intelligence, we and other animals perhaps are the examples that we have. And so getting inspiration or insight from these examples, I think, is going to be key to making progress in AI.
Thank you. There's one more question from Garrett Michener, where he claims that it's continuing a question from Ryan Amaral. Is it possible to have human-like intelligence without a human-like body and environment? Some of our intelligence builds on visual processing, which builds on features of the physical world and vision, such as paths.
Yeah, so this is the question about sort of embodiment. And as I said, this is a debate that's been going on for millennia. How embodied is intelligence? How separable is it from any particular body? And you could argue, you know, I've heard arguments in both directions. One is, you know, that we're essentially very embodied. This is sort of the argument I was making in the talk with respect to, say, the work of Lakoff and Johnson and others. But other people have said, well, you know, a lot of intelligence is sort of separable from the body. It's not body specific. it can be attained without any kind of body. So I don't know the answer. My instinct is that there's a lot about embodiment that we're unaware of, but is actually quite essential to our intelligence. But this is something, again, that we have to understand more about our own intelligence to determine the importance of this for AI.
Thank you again. There is also one question that somehow refers to the recent deep learning models and metaphors that, to my knowledge, you are also interested in. So it's a question from Dylan Banarse. Large language models like GPT-3 show some surprising ability to generate analogies and metaphors. What can we do to determine whether they are actually learning concepts?
That's a great question. And that's actually something that I'm working on myself, is trying to understand the extent to which GPT-3 and other large language models have learned concepts. It's you can probe these systems in different ways. And a lot of people have, and they seem very intelligent sometimes, and sometimes they don't. It's very clear that they have not learned concepts in exactly the way we humans have, but they do have some surprising abilities that we're trying to figure out sort of exactly where those come from. So I would say it's still an open question. I don't think they have learned concepts. They don't have, because I think of concepts as sort of these simulatable models of the world that we have in our heads that allow us to predict something that's going to happen by simulating them. It seems clear that these large language models don't have that, but they do. It's amazing how much sort of learning from billions of words of text can produce the illusion of this. So I would say it's still kind of an open question to show, that whether they actually have learned something like a concept or not.
Yes, thank you very much. I'm looking here if there are any more questions live from the audience, but at least not at the moment. Of course, yeah, the questions technically are still coming in, but we don't want to stretch your patience in a sense, and because of course the discussion took already like over 20 minutes, I think. Perhaps the last question from Stefano Roberto. What can we do, in your opinion, to make clear that narrow AI is limited and to make clear that narrow AI is limited and that can become very dangerous in applications where human understanding is very important? An example could be autonomous weapons.
Right. So I think they're asking sort of how can we convince kind of the public or policymakers about this? And this is a big challenge, right? Because there's so much hype out there about AI. There's so much kind of, you might even call it like misinformation or over exaggeration. People really don't have a clear sense of what the field can do. So that was one of the motivations for me writing my book, was trying to say, like, what actually is the state of AI? How good is it? How limited is it? And trying to write it for a general audience. That's, one thing that we can do as researchers is write for the general public, give lectures for the general public, try and do more public outreach about the state of our own science. That's actually sort of trying. It's hard to get coverage like in the media for things that are sort of not hyped, saying like, well, these hyped things aren't really true. But that's all. I think that's what we all have to try to do. So I think we all as scientists have a responsibility to communicate to the public and to policy makers in our own countries about what the state of our science is.
Thank you very much. So I think this moral declaration, so to say, is an excellent way of finishing the discussion and ending your question, the session. For your information, the questions are still coming in. So definitely your talk attracted a lot of attention. I don't know, Franz, would you like to ask another question from you, perhaps? I don't know.
Oh yes, perhaps I have one last question, and sorry for being out, but sometimes technical problems, if something doesn't work, then you are gone for 5 minutes. Perhaps, still, indeed, I've got one or two questions. The one question is, I remember, I think, I don't know to whom it goes back, I think to Gödel or somebody, who says, it's unclear whether you can really recognize yourself. Whereas there's some idea that a stone can never really understand the concept of a stone, and a bug never will understand how the bug works, or bacteria, not a bacteria. But you promised us, or you told us that you expect that after 100 Nobel Prizes, we can understand what intelligence is. And by understanding what intelligence is, we can create artificial intelligence. So do you really see a chance that we can understand what we are? Or is this really a goal that is so far away, though the Nobel Prize is so far away that we can leave it to our grandchildren and probably never reach it, because that would mean we would understand ourselves, what we are. And this is not really possible because the stone also does not understand the concept of a stone.
Yeah, that's a very deep philosophical question. Of course, a stone doesn't have any concepts because it doesn't have the right architecture to have concepts, but we do. And I do believe that we can understand intelligence. I can't prove that, but I don't think that Gödel's theorem says anything about us not being able to understand that. That's a long discussion to have, but I'm confident that we will understand intelligence. Whether we will understand what we call consciousness, the so-called hard problem of consciousness, I don't know. I don't know if that matters or not for understanding intelligence, but I think that it's a hard problem, but not insolvable. But that's just my own feeling.
Because perhaps to even push on this even further, that if you look at it from a little, for example, Langdon mentioned that the number of Nobel Prizes until now for artificial intelligence is 0. And if you look at the current state, then the machine people, the machine learning people, they promise us they can do learning. But what they basically do is you learn structure in data and you build models for it. And then the learning is perhaps gradient descent. So there's not really much learning and not much intelligence in it. However, although the things you can do with pattern recognition and automatic translation is really great. And then, for example, when you go, for example, to the evolutionary computation people who do a lot of more stuff on this evolutionary learning, then they are doing really good on this learning. But if you really ask them to come up with some systems that don't borrow intelligence from the creator, like most of the machine learning models do, where you borrow the intelligence, but you let really a GP system create something, then we could hardly create a system that is able to sum up more than 5 numbers and come up with a proper result. So we even fail in this. And therefore, if we not even, okay, then this probably emphasizes the point that the number of Nobel Prizes for artificial intelligence is 0, and that the goal that we can really reflect ourselves and come to this fully self-aware AI that has a general purpose solver is so far away that you could hardly reach it.
Well, the Nobel Prize thing was a metaphor, obviously. I didn't mean literal Nobel Prizes, because we don't have Nobel Prizes in AI, but that kind of discovery at that level. I don't know. Science is hard. The the brain is very complex, intelligence is very complex. So I think it's going to be a hard problem to solve, but I don't see any, just because our current methods aren't getting us there. I still think that people will have new ideas and new breakthroughs that will help us understand intelligence a lot better, at least if not perfectly. So, but we'll see in the future.
You're still positive, and like Leo mentioned in his last comment, that at least Bencher, Hinton, and LeCun, they didn't get really a Nobel Prize, but at least a Turing Award. And as there is no really Nobel Prize for the mathematic people, perhaps a Turing Award would also fit. No?
Right.
So perhaps, as Chris has only given me 2 more minutes for questions, then I would perhaps say it's 3 minutes to the beginning of the closing ceremony. Then I would perhaps stop or end the questions. Chris, you're fine with this?
Yes, I think that's a correct right time. Yeah,
then perhaps I want to thank now everybody for asking questions and for having this nice discussion with Melanie. And Melanie, to you, many thanks from us all and from the whole community for giving this very mindful and very also self-criticism or self-critical talk on where the future challenges are. And let's also hope that some of the goals you set up, so that perhaps one of the Nobel Prizes or Turing Awards, they will be awarded in the future, that will get a little closer towards this general purpose AI, but still using, as also the last question moderated by Chris, that we use the general purpose AI for the goodness of humankind and not for specific needs of countries or single people. And many thanks for this interesting discussion, and we are happy. And perhaps one last thing, now let's give you an applause. We are only 2 people, but at least take our applause for this very nice and inspiring talk.
Thank you very much.
Thank you much. It was our pleasure.